Welcome to another Great Cow Basic demonstration. This is part 9 of the tutorials for the 16F171 chip family. Well, hello, my name is Venn. I'm the co-developer of Great Cow Basic, along with a host of other people that make this tool chain work. I'm just presenting to you a series of videos to get the 16F171 family fully understood. But it also touches on a lot more chips. What you can do with this chip, you can do with most chips. It's just that each time we just need to verify, and this verification process is part of these videos. So let's get into the presentation. What we're going to do is we're going to change tack slightly, and we're going to go to use timers. We're going to use timer 0. We're going to use it in 8-bit mode and 16-bit mode, and we're going to flash the LEDs. Up to now, we've been using a timer that's been an estimated timer within the that we calculate within the compiler. But this time, you can use the timer 0 or other timers if you wish, but timer 0 is what I'm going to be using to flash the LEDs. So we're going to set the timers, the internal timers, and we're not going to calculate these within the compiler. So we have to do a little bit more configuration. We're not going to be using the wait command, but as I said, timer 0. The layout that we're using, I'll just turn the video off, is similar to what we had shown on the previous tutorial, and I've left the serial port connections on here. This is by Chris Roper. I'm using a low pin count demo board, and you could do the same. They're available on the internet. So let's talk about what we're going to be doing in terms of the timers. So timers generate accurate time delays, whereas the wait command is an approximation of the time. But you can use accurate time delays. Microcontrollers can measure and generate those required delays using timers or loops in your program. The timer relieves the CPU from operating in the same way as the wait command, and it uses, in these particular chips, a prescaler and a postscaler. A timer is nothing different really, but then a counter. It counts pulses. They can either be internal or external. This chip has an internal, or we're going to be using that, but you could use an external as well. And it increments a specific value, and each time it reaches a maximum value, it will roll over to 0. And a flag called the overflow is set, and that would generate an interrupt if you've enabled it. You can still check that the overflow flag has actually been triggered, but if you set an interrupt, you can handle that through the interrupt vectors. So let's have a look at this diagram. Basically, we have clocks on the left. We have to select it. We select what's called a prescaler and a postscaler, and each time we do that, it scales that pulse. If we've enabled the timer, that will enable the clock to be reset and the timers to count. If they reach, as I said, if they reach the maximum value, it will roll back to 0 and it will set the overflow and interrupt. But we're going to look at that again in a moment in a more dramatic form. So that means if we look at the data sheet, there's a block diagram that looks quite confusing. But in reality, I've highlighted what's important. If you want to use the internal clock signal, that's FOSC/S, 4, sorry, and it's got we need to select that. We need to select a clock 0 prescaler, a value. We need to select clock 0, the postscaler. And then if we're going to check a flag, we have to check a particular T0 IF flag, which is essentially the interrupt flag has been set. There are many other components, but these are the essential lifeblood of setting up a timer. The source, the prescaler, postscaler, and checking a flag. How do we do that in Great Cow Basic? Well, we set up an interrupt. We set up the initialization. We tell it what type of clock source we want, an OSC or external. That's on the first line. We tell it the prescaler and our timer 0 clock source, and then we give it the post scalar value. And in this particular case, it's shown on the screen. I'm going to put a circle around it with my pen. Here, I've told it I'm going to use the internal oscillator, a prescale 256, and I'm using the FOSC4 timer 0 source and a post scalar of 1. I need to start the timer, and then I give it a set timer value. And this time I'm going to give it 9C. And it's a value I'll show you how to calculate in a moment. But essentially, that will set up the prescaler. It will set up the post scalar. It will enable us to set the counter, and I've selected my oscillator source. So we have init the timer, start the timer, and set the timer. But within your Great Cow Basic installation, you'll find a couple of spreadsheet and tools that enable you to calculate with ease these values. I've created these in the past. Essentially, what you do is you set up the chip megahertz that you're using, your prescaler and your post-scalar value, and you give it how much time, the desired value. In this case, it's 10 milliseconds, and it will tell you what value to use, 9C. It's quite simple. It will also tell you down here an estimated real value. In this particular case, it will be 11 milliseconds. And these are all available within the installation of Great Cow Basic. So let's look at that again to make sure we understand. We select the clock source. In this particular case, we're selecting the internal oscillator. It generates a small clock signal. We prescale that, and it makes that clock signal slightly larger. And it scales it. We post-scale that particular signal, and it makes it longer in terms of time. We enable the clock timer. We set our value. We set it to B1, and then remember we set it. The next increment, it will go to B2, B3, B4, etc., etc. And then in an 8-bit timer, it will increment finally to FE. When it gets to FF, it resets back to 0. It will set the overflow flag. And finally, that will then set the interrupt if enabled. So what we see is clock sources essentially growing in time through the use of a prescaler and postscaler. So we've just had a look at how we're going to do it. We're going to initialize things, we're going to start timers, and then set the timers. And we're going to do that with two types of timers, because you can actually set them as 8-bit or 16-bit on these particular chips, depending what level of accuracy you want. So let's have a look at some code. I'm typing in GC Basic. I'm not. I'm typing in GCStudio. Brings up the GCStudio. And then I can take my folder that I've been working in over to my demos. We've still got the camera showing from yesterday. No action in there at the moment. But essentially, I'm going to move into the Explorer. I'm going to zoom in for you, because I do other work when you're not here, by the way. Zooming in, and I'm going to apply the filter, Control F, .gcb, and it will filter out, by selecting the filter, just the Great Cow Basic source programs. I want you to open up, let's start with the 8-bit timer. Example 130, rotate the LEDs using the 8-bit timer. I'm also going to select, but not use initially, example 110, rotate the LEDs using a 16-bit timer. Double click that. We've now got 2 programs loaded, and we can close the Explorer. I only wish I actually clicked it twice. I didn't. 16 bits loaded, and the 8 bits now loaded. Close the Explorer. Here is the 8-bit timer, rotate. So I'm just going to program it, and we'll see what it does on the board. There we go. It's now programmed it. And you can see that the LED is now rotating through the 4 LEDs. So some of the code must be the same as all our previous demonstrations. However, the interval is set via timer 0. So let's have a look what we've got in the code. Chips. It's hash chip. We've seen that all before, but this time it's set to 16 megahertz because we need to control what we're doing. It could be any value. I selected 16, then I did all my calculations upon 16. If you remember, the options for this chip are reviewable in PIC info. Constants, I'm not going to review. They set up the LEDs as outputs. And here we have our program. It says we initialize timer 0 with the oscillator with a prescaler of 256, a timer 0, FOSC4 as a clock source, and postscaler of 1. And if we look at the commentary, it says that these are the prescalers and postscaler values. And what will it do? Here is the value of 9C we saw in the calculator. So I start the timer, I'm setting the timer to 9C, and it will start incrementing 9C, 9E, etc. And when it gets to the right value of 0, we'll be able to detect it. Now, in here, I've set up a little timer called timer counter as a byte. The other LED controls we've seen before, and then into the program. Now this will be every 10 milliseconds, and I want it therefore to do it every 1 second, so I need 100 events. And it says here, wait whilst timer 0 interrupt flag, or TMR0 interrupt flag equals 0. It's wait here until that event is equal to 0. When it's 0, we know the flag has actually, so whilst it's 0, wait here. The moment it's 1, we know the flag is set. We clear the flag, we increment a timer counter by 1. If it's equal to 100, do something. Let's just close that down. If it's equal to 100, then do something. But it's not 100 initially, it's only set to 1. Then it resets the timer back to 9C, which basically says run timer 0 for 10 milliseconds. But when it gets to 100 of these, 100 times it's been through this, it would then rotate the LEDs exactly the same as we've seen before. Won't go into that. And then we just reset our timer counter. Once that's back to 0, it's going to count to 100 again. And once the timer counter is 100, we're back at 1 second, then rotate the LEDs by. So if I change, just for pure example, I change the frequency up here to 64 megahertz, we will see a 4-fold decrease in the time of the rotation of the LEDs, because 16 is a quarter or 4 times less of the 64 value. Let's program it up. And as I said, the value it doesn't do 64 megahertz, and it's telling me that because it only does 32 as its maximum frequency. So we should see the clock, the LED rotate every half a second. And it is perfect. I'll put that back as it should be. So what we've seen is that in a few lines, we can set up the clock, and we can set up the values and start the timers, and we're running. Then we check a flag, timer 0, interrupt flag is set to 1. Eventually, it's not equal to 0 and it's therefore equal to 1, and then we clear it and count. Very simple. How do we do that for a 16-bit timer? Very similar. We set a constant just to inform the compiler we want to use a timer 0 16-bit, and if you look at the block diagram within the data sheet, that actually relates directly to one of the bits that you can set. Again, we set the oscillator source, we're setting the prescaler this time to 64, the clock source with timer 0 to FOSC4, and the postscaler to 1. And that now means that you need to set a very different value because the clock sources are much, much faster. So much faster. We have a much bigger value. We have to set that to 3036, and I've given you a tool inside your installation, and you can calculate these very simply using the tools that are in the demo folders. So we set the timer, and this time we don't have to count so many times because this timer, because we're using a 16-bit timer, will run to 1 second. So therefore, I just say wait whilst timer 0 interrupt flag equals 0. It just sits there waiting. The moment it clears to 1, then I clear it, and then I rotate the LEDs, and then I reset the timer back to 1. Let's program that through. We're back to 1 second, so every 1 second. So what we're doing is essentially setting up timer 0 with a 1 second flag or interrupt. We're checking the state of that flag and then rotating the LEDs. Only 4 things to be done. Well, four essentially. Four things. You need to set up the clock sources, start the timer, set the timer, but you've got to calculate these values. As I've said, they're in the installation for you, and I'll just pull them up, show you on the desktop. Here we have a calculator built in Excel, and I've set the clock source here to 16. I've set my prescaler to 254. My source divider is 4. We know that from the clock source. And we say, right, how long do I want? I want 10 milliseconds. That's 0.01. And therefore, I've got to set my code here to 9C00. Job done. And that's how we get the values. If you change your clock source to 32, it says, oh, you can't have a 1 second delay because it's gone red. Let's see, you can't have a 10 millisecond, you can have a 5 millisecond. Yeah, 5 millisecond, because it's twice as fast. There is a maximum value, and it goes red if you've exceeded it. So if you set this to 16, you're good. 32, you can set the you can set the prescaler to the nominal values you've got available in your chip. Source divider and a postscaler is down here, and you can set that to some of the postscaler values. But this calculator enables you to use a decimal value or hexadecimal value, and it will tell you how fast, how accurate it will get to your target down here. So, wanted to show how to do timers in Correct Basic. I think we've done that. So the next video is actually, I like the next video. It's using CCP with PMW. It is just so simple. With the new style of microcontrollers, I enjoy this one. It's just very simple. We're going to dim the LEDs using CCP pulse width modulation on the next video. And with that, we'll call it a wrap.